All right, this is the final example of writing equations of parallel and perpendicular lines. So we are going to look at modeling a real life example. All right, the question says the planned path of airplane A is shown in the graph. Each grid square represents 1 square mile. Airplane B will fly along a path parallel to airplane A, passing through the point 14,4. Airplane C will fly along a path perpendicular to each of these paths, passing through the point 7, -1. An air traffic controller is in charge of the region represented by the fourth quadrant. Do any of the paths intersect in the air traffic controller's region? All right, so what do we need to do to get started? So the first thing we need to do is figure out what is the slope of airplane A, and we need to figure out what the equations are for B and C. All right, so let's first look at the graph. We can look at the graph. We can do rise over run, so we can do 1, 2, 3, rise 3, run 2. So airplane A has a slope of 3/2. All right, 1, 2, 3, 1, 2. Rise over run 3/2. All right, so it says the planned path of airplane A is shown in the graph. Each grid square represents 1 square mile. Airplane B will fly along a path parallel to airplane A. All right, so B is going to be parallel to A, which means it will have the same slope. All right, parallel lines, remember, have the same slope. All right, so airplane B will fly along a path parallel to airplane A, passing through the point 14,4. All right, so let's go ahead and look at airplane B first. All right, so we know our equation. Again, if you don't know point slope form, commit that to memory. Y minus, my y value is 4, equals 3/2 times x minus 14. All right, I'm going to go ahead and rewrite this. So y minus 4 equals 3/2 x. All right, let's see. 3/2 times 14. Let's see, 14 times 3 is what? 43, I think. Let's see, 14 times 3 is 42, and then divided by 2 is 21. So 3/2 times -14 is -21. Add 4 to both sides. Y equals 3/2 x minus 21 plus 4 would be -17. And that would be my equation for flight or airplane B. So this is B. All right, now C. Let's see what C says. All right, airplane C will fly along a path perpendicular to each of these paths. All right, so we know that perpendicular lines have a reciprocal that's a negative reciprocal. So 3/2, remember, a negative reciprocal, you're going to flip it and change the sign. So -2/3. So now I know if I multiply these two together, they would equal -1. Those are considered negative reciprocals of each other. All right, so I have the slope of airplane C, and it passes through the point 7, -1. All right, so again, I'm going to write an equation. Y minus, my y is -1, equals m times x minus, my x is 7. All right, so minus a -1 would be y plus 1 equals -2/3 x. -2/3 times -7 would be positive 14/3. All right, if I subtract 1 to get a common denominator, I have to subtract 1, but I'm going to subtract 3/3. Hopefully you remember that 3 divided by 3 is the same thing as 1. So to subtract 1, or to subtract fractions, you have to have a common denominator. All right, so 14 minus 3 is going to be 11. So 11/3. All right, so this is my equation here for airplane A. And I need to graph B and C. So let's just quickly graph this on the calculator and see where these lines go. All right, y equals 3/2 x. So let's do 3/2 x minus 17. And then I'm going to graph negative 2/3 x plus 11/3. Let's hit graph. All right, so if we want to change this window to look like this, we can change this over here. It looks like we need to go out more on our x's. So let's just change our window a bit. So our window, we don't really need to go negative 10. Let's just go negative, say, 2. All right. Now our x maximum, that is where our lines are. So let's extend that out to, say, 20. And our y's minimum and maximum, we can leave those for now. Excuse me. All right, so that just kind of zooms it in the window. Makes it a little bit nicer. All right, so if you remember, the one with the positive slope, the 3/2 x, that's the blue line. That one is B. That's the one that is parallel to A. And then the red line here is going to represent line C because it has a negative reciprocal slope here. So you can see that airplane A would be in this region, and also it's going to have this perpendicular line from C that comes through that as well. All right, let's see if I'm going to write an equation real quick for airplane A so that we can also graph it on the calculator so it'll make it easier to see when they're all on the same graph. All right, so we can see that we have a slope of 3/2, so we can go down 1, 2, 3 over 1, 2, and we know that our y-intercept there is -5. So very quickly, I can write an equation. Y equals my slope minus my y-intercept. All right, so that represents A. All right, so now let's graph A. All right, 3/2 x. So it's just easier to see when they're all in the same, on the same picture. Okay, so now you can see the two parallel lines and we can see the one that is perpendicular. All right, now it says an air traffic controller is in charge of the region represented by the 4th quadrant. Do any of the paths intersect in the air in the traffic controller's region? All right, so remember when you have a graph, you're not seeing all the quadrants right here, a little bit of these quadrants, but remember your quadrants start in the positive. So this is quadrant 1, quadrant 2, quadrant 3, quadrant 4. So quadrant 4 is this bottom region right here. So it says an air traffic controller is in charge of the region represented by the 4th quadrant. Do any of the paths intersect in the air in that region? All right, so these two intersect in region 1 or quadrant 1, but these two intersect in region 4 or quadrant 4. So the graph shows that the paths of airplanes B and C intersect in the air traffic controller's region. So that's what you can conclude by looking at the graph of those lines. All right, if you have any questions, please let me know.